Researchers at the University of Washington demonstrated the first human-to-human brain interface when one participant sent a motor command over the internet to trigger a physical response in another person. This bypasses the traditional peripheral nervous system entirely. Electroencephalography sensors capture the electrical noise of the brain through the scalp. High-density electrode arrays identify specific oscillations, like mu rhythms, which change when an individual imagines motor movement or sensory input. Raw neural data is processed through noise reduction filters and spatial Laplacian transforms. Machine learning algorithms then classify these patterns into binary commands, allowing a computer to interpret human thought as discrete digital signals.
Information enters the receiver brain via transcranial magnetic stimulation. A copper coil creates a rapidly changing magnetic field that induces an electric current within specific cortical neurons through electromagnetic induction. By stimulating the visual cortex, researchers can induce phosphenes, which are flashes of light perceived without any external visual input. This allows for the transmission of simple shapes or Morse code directly into a subject's conscious perception. BrainNet represents the first multi-person, non-invasive, direct brain-to-brain interface for collaborative problem-solving. It utilizes a sender-receiver architecture, where participants transmit information to a central brain to solve a visual task together.
Current non-invasive systems suffer from extremely low bandwidth, often limited to less than 10 bits per minute. Increasing this transfer rate requires better spatial resolution in stimulators and higher signal-to-noise ratios in sensors. Transcranial focused ultrasound offers a higher spatial resolution than magnetic stimulation. It can target deep brain structures with millimeter precision using acoustic energy to modulate neuronal excitability without surgical intervention. Effective telepathy requires closed-loop systems, where the sender receives immediate feedback of the receiver's state. This creates a bidirectional flow of information, allowing for real-time correction and synchronized neural coupling.
Repeated transcranial stimulation can induce long-term potentiation or depression in targeted circuits. This means brain-to-brain links could potentially be used to accelerate learning by physically strengthening neural pathways via external induction. Brain-to-brain interfaces allow for sensory substitution, where visual information is translated into tactile or auditory cortical stimulation. This permits a person to feel what another sees or hear what another touches. As neural links become more complex, the risk of unauthorized access increases. Future systems will require neural firewalls to filter outgoing thoughts and encrypt incoming stimulation to prevent cognitive hacking or involuntary manipulation.
Direct neural integration challenges the concept of the individual self. Continuous high-bandwidth connection between multiple minds could lead to a collective consciousness, where thoughts and memories are shared across a distributed biological network. The emergence of telepathic technology necessitates legal frameworks for cognitive liberty. This includes the right to mental self-determination and the protection of the inner sanctum of the mind from state or corporate surveillance. Neural interfaces may eventually bypass the bottleneck of symbolic language. Instead of translating thoughts into words and back into thoughts, we could share raw conceptual frameworks and emotional states directly between brains.
Brain-to-brain links offer revolutionary potential for treating neuropsychiatric disorders. A healthy brain could theoretically act as a neural pacemaker for a dysregulated one, providing the correct firing patterns to stabilize mood or motor function. Future transhumanist applications include direct skill transfer. By recording the neural firing patterns of an expert and replaying them via transcranial stimulation in a novice, we might reduce the time required to master complex physical tasks. While current research focuses on non-invasive methods, high-bandwidth telepathy will likely require invasive neural lace or microscopic electrodes. These interfaces provide direct access to individual neurons, allowing for millions of simultaneous data channels.
Sharing the raw neural correlates of emotion could foster radical empathy. Experiencing the literal pain or joy of another person through direct stimulation eliminates the barriers of subjective interpretation and could fundamentally alter social structures. Linking minds via transcranial stimulation is a stepping stone toward post-biological existence. As neural data becomes fully digitizable, the distinction between human thought and machine intelligence vanishes, leading to a planetary-scale integrated intelligence. Focused ultrasound works by altering the mechanical tension of neuronal membranes. This affects the opening and closing of ion channels, which modulates the probability of action potentials without the heating associated with other stimulation methods. Temporal resolution is critical in brain-to-brain links. Information must be delivered within milliseconds of the relevant neural window to ensure that the stimulation is integrated into the ongoing cognitive process of the receiver. Researchers use frequency modulation and pulse width modulation to encode complex data into magnetic pulses. These strategies mimic the natural spike timing-dependent plasticity of the brain to make artificial signals more recognizable to biological circuits. Telepathy could redefine labor by allowing groups to merge their cognitive resources on specific problems. This distributed neural processing could solve complex scientific challenges at speeds impossible for any single human brain to achieve. Biological brains are noisy and prone to error. Neural interfaces must incorporate redundant data streams and error correction algorithms to ensure that the transmitted thought is decoded accurately, despite the inherent variability of brain activity. When two minds collaborate via direct link, the legal ownership of resulting ideas becomes ambiguous. We must develop new intellectual property laws that recognize the collaborative output of integrated neural networks rather than individual creators. Direct brain stimulation carries the risk of sensory overload. If the incoming data stream is too intense or poorly filtered, it can trigger seizures or cognitive fatigue, requiring sophisticated throttles to manage the rate of information influx. The final stage of this technology is the Internet of Brains. This global network would allow for the seamless exchange of information across billions of individuals, creating a new layer of the biosphere known as the noosphere. Access to neural enhancement technology could create a cognitive divide between the enhanced and the unenhanced. Ensuring equitable access is a fundamental challenge for society to prevent the emergence of a new species-level hierarchy. Brain-to-brain telepathy is transitioning from science fiction to laboratory reality. While non-invasive transcranial stimulation is currently in its infancy, it paves the way for a future where human minds are no longer isolated biological islands. Advanced neural decoders now use recurrent neural networks to predict intent from noisy scalp data. These algorithms can differentiate between subtle differences in thought, such as the desire to move a specific finger versus the entire hand. Optimizing brain links requires precise control over pulse frequency, intensity, and duration. High-frequency stimulation typically increases cortical excitability, while low-frequency stimulation tends to inhibit neural activity, allowing for versatile control of the receiver brain. Neural synchrony is the measure of how well two brains are aligned. In successful telepathic links, we observe phase locking, where the rhythmic electrical activity of the sender and receiver brains begin to oscillate in perfect unison. While current technology focuses on motor and sensory data, the long-term goal is memory sharing. This involves stimulating the hippocampus to evoke specific episodic memories or to store new information directly into the long-term memory of the receiver. The main bottleneck for non-invasive systems is the skull, which scatters electrical signals and dampens magnetic fields. Overcoming this requires sophisticated beamforming techniques and hypersensitive sensors that can detect minute magnetic fluctuations. Telepathy will fundamentally change social interactions. Hidden intentions and deceptions become difficult to maintain in a connected mind environment, leading to a society based on radical transparency and immediate shared understanding. Integrating haptic feedback into BBI allows the sender to feel when the receiver has successfully processed the information. This tactile confirmation loop significantly improves the accuracy and speed of collaborative neural tasks. A comprehensive neuroethics framework must address issues of agency and responsibility. If a receiver performs an action based on a transmitted thought, who is legally responsible for the outcome? The sender, the receiver, or the system architect? Brain-to-brain links can be used to augment human intelligence by connecting to external artificial intelligence. This hybrid system combines biological intuition with machine processing power, creating a new form of symbiotic superintelligence. The development of brain-to-brain interfaces marks the end of biological isolation for the human species. We are moving toward a future of unprecedented connectivity, where the boundaries of the individual mind finally dissolve into the collective.